I was going to say as a part of my introduction that I am a very new assistant professor, so I still kind of, when I'm introducing myself, have to remind myself to say assistant professor rather than PhD student, but Michael already did that, so that's great. So today I'm really excited to talk to you all about leveraging social theories to enhance human-AI interaction. Let me make that a little bit more concrete to begin with. So I leverage theories about an understanding of how people think, communicate, and collaborate to design effective and safe human-AI interaction. I'll share more about this as I answer 3 questions during this talk. What is an effective human-AI partnership? How can we make human-AI interaction safe? And what can we do to enhance human-AI interaction going forward? So let's start with the first question there. What is an effective human-AI partnership? Effectiveness to me is about combining people and AI in a way that takes advantage of what they're each good at. So I'm going to give you a very brief example of this for the setting of visual question and asking. So not a deep dive, just a quick overview of what I mean here. So visual question asking starts with a visually impaired user sharing an image along with a query online and trying to get an answer about what's in that image. So some examples of this are, what color is this? Or what item is this? Because they can't see their environment, they're trying to get these answers by asking them online. Now these questions with these images are fairly easy to answer, especially with recent advances in computer vision, but things can get tricky very quickly. Now visually impaired users can't always see the environment that they're taking a picture in, right? So they can share potentially sensitive content online. So for example, someone might ask, which medication is this? And instead of just sharing the medication packet, right, they can share a prescription bottle with their name or their address on it. Or someone can share a random image from their gallery with their face on it, right, and that leaks information about them online. So what do we do here? How do we prevent visually impaired users from sharing private content online, but also still be able to get answers to their queries, right? One way to think about a solution is, can we obfuscate, pre-process the image in some way so it hides this potentially sensitive content? So for example, if this is your original image, can you obfuscate it to maintain the context but not share what's private? Right? Now this task is really hard for people or AI to do on their own. AI doesn't always understand what we mean when we say private or sensitive, so it can't automatically do this task. And people aren't a very reliable way of doing it either. In both cases, whether you try to use people or AI individually, you have to share the original image with them, which sort of defeats the purpose of the task itself. So to solve this problem in sort of a human-AI effective partnership way, we divided an image into segments, and then we had crowd workers look at one segment at a time. So instead of seeing the full image, they just see a little segment. Now, people are really good at understanding context that AI isn't. So when I see a nose in that segment, I can sort of guess that that's probably a face in the surrounding segments and mark them, guess them as sensitive as well, right? And we used AI for this task to optimize for a certain budget that users provided, and also making real-time decisions around which segments of these need to even be shown again to different crowd workers to make a decision about their sensitivity. So that's what I mean when I say an effective human-AI partnership. We started them with small segments, and we progressively had them label larger segments that were already masked to get to this image on the bottom left that was then sent to third-party Q&A websites to get answers to people's queries. I've done this sort of effective partnership of people and AI in different types of domains, visual Q&A, workplace settings, for data science. And in all of these, the question that comes up next for me personally is, well, what about real-world deployment? Right? We're trying to build these systems for research, but ultimately we want to put them in front of actual users in the wild. And that's not quite as easy as just taking the research system and then making it available to everyone, right? There's a lot of additional considerations that we don't think of when we're building them as research systems. So for example, for the Q&A, visual Q&A system that I just talked about, right, you have to consider bad actors. there might be crowd workers that would work together on a sort of forum and adversarially attack the system to get all of the image segments back from it, right? So there's things that you can't anticipate. And now you might think, okay, that's a hypothetical, bad thing that could happen. But there's a lot of evidence of how when human and AI systems are deployed in the wild, bad things can happen. Biases that we haven't considered or harms that we don't think about can come up in these settings. So in my research, this effectiveness is just one piece of it. There's this whole conversation around safety when you think about deploying these systems in the real world. And in my research, I try to bridge that delta between innovation and effective deployment in the real world by thinking about safety. And this includes two questions about, first, understanding what's wrong, understanding the incompatibilities that are at play that cause harms and biases in the wild, and then also trying to address those incompatibilities. And that's what I'm going to talk about next with sort of how do we make human-AI interactions safe. But before I do that, any questions so far? I'm happy to answer clarifying questions as I go and then leave big questions for the end. Okay, so luckily, I'm not the only person trying to study how to make human-AI interactions safe. There is a major thrust of research on interpretability and explainability, with the idea being to help people understand AI and machine learning systems that are deployed in the wild. And the assumption there being, if we can help people understand what these complex AI and machine learning systems are doing, then maybe we can stop potential harms before they happen, or potential risks before they're put in systems. There are two major approaches to this. There are glass box models that are inherently interpretable, where I'm very quickly able to tell how a set of input features leads to a predicted outcome. And then there are black box models where you can't really tell what the machine learning model is doing, but the community has developed post hoc explainers for these models that approximate their behavior and so are able to give you some idea of how a set of input features leads to a predicted outcome. With these approaches, you can normally get three types of visual outputs. So say you were predicting income based on demographic data, you could get a local explanation. This tells you how a single prediction was made. So on the y-axis here are values of a single individual, and then you can see how they shaped the final predicted class of income. Here at 0, 0 just means less than 50K income. You can also get specific feature explanations which tell you how a single feature affects the predicted outcome. So here you can see how age impacts income across all data points in the data set. And then if you do this for all features being used, then you can get a global ordering of what the model considers important overall, what it learns about the data set and all of its features. And that's called a global explanation. So these explanations provide insight into model behavior in AI that we did not have before. But the question that remains is, does this work in practice? Do people who use these systems then are able to make better decisions about the data and the model? And that was one of the questions that we wanted to tackle in this project that we did. This was one of the first human evaluations of these tools in practice, which was done with data scientists. Data scientists, because they have some machine learning expertise already, they know the machine learning concepts we're talking about here. So we started with nuanced sort of qualitative interviews to understand the challenges that come up in the data science pipeline. We followed this up with synthesizing these challenges into a data set and then running contextual inquiries to understand if people were able to use interpretability tools to resolve these challenges. And then we wanted to quantify those findings, so we conducted a large-scale survey to see if those findings from our contextual inquiry held up at a large scale. Unfortunately, what we found was that interpretability alone does not work. Rather, people misuse and overtrust interpretability and explainability tools. So less than 4% of 197 data scientists in our study could accurately describe what these visual explanations could do or what they were trying to tell us, right? Most of them overestimated the capabilities of interpretability tools. So here you can see on the y-axis various different capabilities of interpretability tools, and we had asked people to select all that apply to the tool that they were using in the study. Of these capabilities, only the ones in these bounded boxes are were actual capabilities of these tools at the time of the study. And as you can see, people assigned a lot more value in terms of capabilities to these tools than was actually possible at the time. And some of these are things that are realistically not going to be possible for a long time, like automated detection of fairness issues. No tool is capable of automatically understanding all fairness issues in a system. Most data scientists gave our erroneous model that we had shared with them very high deployment scores. So they said, oh, you could deploy this in a loan application being used in the wild, right? You could do this right now with the data and the model that you have. Now, again, like I said, we had synthesized some errors in the data, right? So as a result, one of the visuals that people saw was this. So what we had done was impute 10% of the age values in the data set with a mean age. As a result, around that mean age of 38, 39, you see a huge spike in the relationship between age and income, right? So we had synthetically introduced this error and several others. And we were hoping that after seeing these visuals with these errors, people would say, well, this model is not ready for deployment. But most of them gave it a score of, on average, 5 on a scale of 0 to 7, so they thought it was ready. They came up with narratives to justify the spike. Right? So one thing that a lot of the participants in our study said, well, around 38 or 39 is when you pay off all of your loans. So you're actually taking all of your income home with you. So the spike makes sense, right? So they came up with these narratives to justify what was being shown by the tool, rather than using it as an evaluative device, right? So interpretability, as currently designed, does not work. The solution that is intended to help make human AI systems safe for deployment doesn't quite work. Now, naturally, the next question that comes to mind is, why, right? What's going on here? And that was sort of the question that we wanted to ask as well. And again, we wanted to study this in we wanted to not just think of interpretability as a technical solution, but think of what social, human-centered factors might be at play. So we hypothesized that the bounded nature of human rationality was what was going on over here. So there's a cognitive framework called bounded rationality, which essentially says that cognition is expensive, so people apply heuristics as shortcuts to make their decision-making easier. Our brain has two systems, system 1 and system 2. System 1 is sort of an automatic, intuitive, and unconscious thinking mode. It's fast, but it can be error-prone as a result. System 2 is a more slow, controlled, analytical, and deliberate thinking mode. It's reliable, but it requires significantly more cognitive effort. And research in psychology and cognitive science has found that people rely far more on system 1 than system 2 in their day-to-day lives. So to quickly make decisions, people apply heuristics. For example, there's the availability heuristic, where they use immediate examples of something that come to mind rather than taking in the full picture. And the things that come to mind immediately are usually based on frequent examples or recent examples or vivid examples in your life. Another heuristic that people apply is imitate the majority heuristic, where they go with choices that are popular in their socially proximal sort of reference group. So for example, when you're ordering food on DoorDash, how many times do you look through all items on the menu versus selecting, a popular dish from a restaurant? So we want to see, well, what does this look like for machine learning? How do you define bounded rationality for machine learning? Now, this is where I have an example notebook that you're welcome to go to and try out sort of things on your own. I'll mention visuals that are important from that notebook here in a second, but again, you're welcome to play with that. Okay, so that notebook will take you to an example of using the Titanic survival dataset, very important dataset that tries to predict, based on passenger info, whether someone survived the Titanic or not. So in the notebook, you'll see the dataset, the model, and an explanation tool called SHAP. And these are some SHAP visuals that you can see in the notebook or here. So here's the global explanation. this is sort of the ordering of features that the model thinks globally across all data points is important about Titanic survival. Here's the relationship between the sex and survival. Here's the relationship between age and survival. And this on the bottom right is one single data point. So this is one passenger's information on the y-axis here. And you can see how each of those information pieces made an impact towards the final prediction of survival for this passenger. Now I'm going to ask you a question that data scientists often have to think about. What would make this prediction go from 1, which is this passenger surviving, to 0, not surviving? Very morbid example, I know, but we're going to talk about how we can flip the prediction for this bottom right passenger from surviving to not surviving. I'll even give you some options. You could change the cabin value from D35 to E67. You could change the fare from $52 to $10. You could change the age of the passenger from 37 to 70. Or you could change the sex from male to female. So which of these changes, or more than one, do you think would flip the prediction for this passenger on the bottom right to not surviving? They currently survived, but we're wanting them to not survive. So take a couple of minutes, feel free to throw answers at me. I saw someone already say 3, changing the age from 37 to 70. Feel free to discuss if you want, and we can come back in a second here. You're running the code. This is a very important data science problem, I know, so I want you to really think about it. All right, show of hands. How many of you think 1 is the answer? All right, nobody for 1. How many of you think changing the fare will flip this prediction? Maybe a couple here and there. How many of you think it's 3? Wow, that's a majority. And how many of you think it's 4? A couple, okay. All right, so like I said, we're making this passenger not survive the Titanic. So unfortunately for a lot of you, only 1 and 2 are accurate. So 1 is a little bit hard to reason about unless you really care about the schematics of the Titanic and have done in-depth sort of deep dives into it, right? I don't know what cabin is where in the ship, so it's hard to reason about that, right? But it is accurate. I did run it. 2 is a little bit easier to reason about, right? If you reduce the fare, this passenger potentially is in a lower class cabin, right? And lower class cabins were hit first. So you can reason about that. 3 is also very easy to reason about. You increase someone's age, maybe makes it harder for them to get to the lifeboats. Again, I said this example was morbid, so I'm not going to take any responsibility for what I say here. But in this case, for this passenger, the age does not matter because the passenger class, being first class, was a mediating factor. And then 4 is inaccurate because females survived the Titanic more than males did. So both 3 and 4 are actually inaccurate. Now this exercise that we just did here, this type of applying your heuristics, right, to solve a problem, we figured that data scientists do this all the time in the data and machine learning and AI use that they do in their jobs, right? So we wanted to see to what extent do data scientists, pick accurate answers, or to what extent do these heuristics and biases come to play and they pick inaccurate answers? So to make this entire setting a little bit more formal, we have these axes to propose quadrants for bounded rationality. The axes are time and cognitive effort because that's what has been used in the past to study bounded rationality in decision making. Now, when you apply deliberate reasoning, like for those of you who maybe opened up the schematic of the Titanic to figure out where the cabin was, right? When you deliberately think about something and spend time on it, it's called maximizing your cognitive mode, right? And we felt that in the interpretability setting, given everything we know about overuse of interpretability tools, this would be the control condition without any interpretability. Now, again, because of what we know about interpretability already, we felt like the opposite, where you don't spend a lot of time and cognitive effort in your decision making, the satisficing cognitive mode, would be where the visual explanations that you just saw would land, right? So these are the visual explanations, static visuals from interpretability tools would fall under that category. Now there's the cognitive mode where you have to make very quick decisions, but these are also very critical decisions. So settings like healthcare, where you're really, as a doctor, making decision about patient survival. So we call this the survival cognitive mode. Luckily, data scientists rarely operate in that quadrant, right? They often have more time with the data. So this wasn't one of the conditions in our study. And then that's what I like to call the optimizing cognitive mode, where you're spending a lot of time with a system and interacting with it and engaging with it, but it's not cognitively effortful. You're enjoying spending time with the system. So one thing we learn in HCI is to sort of have that kind of interaction. You can make a system more interactive, more fun to use with different kinds of features. So we hypothesized that if there were interpretability tools that weren't just static visuals, but had more interactive features, they would fall under that mode. And there are tools that do that. So here's an example of Google's What If tool. So using Google's What If tool, you can bin, color, scatter plots using sort of different cohorts of data, as you can see here. You can also look at counterfactuals for a single data point. So you can kind of see what the nearest counterfactual is. You can see partial dependence plots for the feature relationship with the output. You can see how each individual prediction was made, what was important towards that prediction, change these values in real time and get sort of real-time predictions with updated values for a data point. So there's a lot more you can do with this tool than sort of the static visuals that we saw before. And this is just under the data point editor. There are other tabs for performance and fairness metrics or different types of feature information that this interactive tool allows. Now, it isn't that the information that forms the basis of the decision-making that we did with the static tools has completely changed. The information is the same. The visuals that they're using, the three types, are still primarily the same. It's just that they've added interactive elements on top so you can change things more quickly, get a reactive sort of feeling with the system. So we ran a pre-registered control experiment. It was between subjects. It was with data scientists, about 119 of them, where we tested their performance between these conditions that I just described. We had a control condition and two conditions each for visual explanations, the static outputs, and the interactive tools. Why two? Because we were testing a glass box model, a glass box approach, and then a post hoc explainer for a black box model. The setup was very similar to the Colab notebook that I shared with you all. They could access code, they could write code, they could access any visuals they wanted. And in parallel, there was a Qualtrics setup. Qualtrics is a survey platform. So they answered multiple choice questions about the data and the model on Qualtrics. We had also provided hints throughout the study because in running a study, you have to be careful about not making the task so cumbersome that participants can't solve it. So that was the high-level setup. Any questions before I get into even more detail? Yes?
Yeah, the control,
Yep.
can you just explain a little bit more of what that actually looks like? Is it just like they're just going through like data sheets or like what is that?
It's just we give them a notebook with just the data set loaded and a machine learning model.
Okay.
No interpretability. Any other questions? Yes?
For the control group to know what tools they have available, like what's their experience, was there a specific criteria?
Yeah, so like I said, it was just the data and the model in a notebook, so they could write their own code on top. We did give them links to potential explanation outputs, but we did not give them the code. In the other notebooks, those explanation outputs were sort of embedded in the notebook by us already. The interpretability tools were already embedded. In the control condition, if they wanted those types of outputs, then they would have to go to the links that we had shared, read the documentation, write their own code, and then get those outputs. But that's a good question that leads into the results a little bit. All right. So to study bounded rationality, to measure whether it was happening, right, we had some proxies. There were process-level proxies that we wanted to measure. These were predictably time and cognitive effort, which have been all about the axes that we had designed to begin with. We also included the number of hints people used during the study as a way of measuring whether they were applying bounded rationality. And then, of course, there's the outcome, right? What happens as a result of the application of bounded rationality in the setting? So these were things like the accuracy of people's answers about the data in the model, and then the types of answers they selected. So in the exercise we did, there were some options that were purely accurate, some that were plausible that we could reason about, but maybe accurate or inaccurate. And then there were answers that were purely inaccurate. There was no plausible reason for them to be accurate, right? So we had these categories of options in our multiple choice questions that we also studied as part of the quantitatively defining bounded rationality. So to study our continuous variables, we used one-way ANOVAs and Tukey HSD as a post-hoc test to study them quantitatively. And then for our categorical variable, we used chi-squared, test of independence. I'm going to mention 3 of these in the results, just in the interest of time. So let's look at the time spent on task. Now, as you can see here, people in the control condition spent far more time on the task, significantly more than any of the interpretability conditions. So just as a basic thing, it seemed like, people in the interpretability conditions spending less than 5 minutes on task were clearly applying some way to make the task go faster compared to a control condition without any interpretability. Somewhat, and I should have said, it's 5 times more time spent on task in the control condition. Now, maybe somewhat as a consequence of that, for accuracy, control also had the best numbers. People in the control condition were at least 17% more accurate than those in the interpretability conditions. Interpretability tools, whether they were static or interactive, did not seem to help. Yes?
What's chance accuracy here?
Chance?
Yeah, like everyone's doing, most of the conditions are doing below 50%.
Yeah, it was, we had 5 conditions, or 5 questions, 5 options each, so 20%.
So 20% would be
yeah,
what I'm guessing?
yeah. Okay. And then, of course, if you look at the residuals from our chi-squared test, they also showed the sort of significant directionality of people in the control condition picking accurate answers compared to the other conditions, which leaned more towards the other types of answers. So overall, our results from our experiment, just to sort of mention them in the context of this quadrant that we started with, were pretty expected for the satisficing conditions. The people who were using these static visual tools were satisficing. They were spending less time, less cognitive effort. What was surprising was the interactive tools conditions. We had expected that people would spend more time on task and maybe get to more accurate answers using these interactive tools. But in practice, these sort of fell in the surviving quadrant instead. And I'll mention my hypothesis why. Right? So for the static tools, we had thought these make things look so easy in the form of just these static visuals that people end up applying their cognitive heuristics instead. For the interactive tools, it was the opposite. They are so complicated. There's so many features, so many toggles, so many interactive elements, right, all coming at you at once, that people applied their own heuristics as a way of not doing this cognitively burdensome task. Instead, our control condition seemed to be more closer to optimally effortful than we had expected. And I think this is because of the question you asked before, where people did want interpretable outputs, right? And they would have had to read documentation and write code to do it. And we provided them with just the right amount of information on which code to implement, right? We gave them the link to the right thing that they could then use to kind of implement and have in their notebook as an answer. So that's why we feel it was maybe closer to that optimally effortful condition that we were hoping interpretability would be. So that's sort of our hypothesis for what's not working and why, right? The bounded rationality is at play, that current interpretability tools don't really take it into consideration, don't really account for the fact that people apply heuristics and biases. I want to do another quick pause there if anyone has any thoughts, comments, questions.
I was in the control study, like, if the people did add interpretability tools, and which ones did they tend to?
So it was different in that we did not want to give them the same tool as the other conditions because those were heavy-duty, full sort of feature interpretability tools that would have required a significant amount of work on their part. Instead, we gave them links to codes about similar explainers. So if you wanted to get feature attributions like the global explanation, here's an equivalent that looks similar. So sort of similar, but not the same tools. Yeah.
How many approximate percentage of people that were actually implemented those tools? Because you had a very large standard deviation.
Yeah, you're right. The standard deviation is pretty large, and that was sort of one of our concerns as well. So of the 22 people in that condition, I believe the number was 14 who actually wrote code for the tools that we had linked. But in addition to that, the other participants still wrote code. It was just not implementing what we had linked them to. So all the people in that condition wrote some kind of code.
Would you expect the results to be different if participants had enough, or were under a time constraint, or had enough time to work through these tools on their own?
So we did not have any time constraint in the study. The only time constraint was that it was a study, so they were taking time out of their daily practices to do the task. But what we were surprised by was this inclination to quickly find answers that interpretability conditions were sort of serving, right?
The people that were using the tool knew about these tools, so they knew how to work with them, or they had to learn, or you gave them a tutorial before using the tool?
Good question. So we had people with prior experience in machine learning and interpretability in general in the study, not the specific tools, but we did give them a tutorial and information about the tool before the study, before we started measuring the time they were spending on things.
The reason I'm asking that is because I think these people may have trusted the tool over the outputs because they don't know how it actually works.
Right. So as far as we know, well, I guess we didn't really get into, since the conditions were randomly assigned, we didn't really ask about specific tools that people had used before. But the only thing we sort of know going in is that they had some machine learning experience. And then we gave all of them the same kind of basic training on how to use the tool. So whatever inferences they made about that training, about the tool through that training, you know, there's going to be variance that's sort of covered in the number of responses. Yeah. I don't know what order people were asking questions in, so I'm going to go here. Sorry.
I guess in a similar vein, how do you think these results would change if it were for a more general audience or people with less technical expertise?
Yeah, you know, that's a good question, and my expectation is the interpretability results will be worse because not everyone knows how to code. So in a control condition without any interpretability, having to do that coding task might not be feasible for everyone, right? So people would over-rely even more so on the interpretability outputs. And that's sort of my worry, is that if people with machine learning experience can't always distinguish or use these tools the right way, then what can we expect from, you know, lay end users who don't even know how a model works or what goes into the process?
Coming up with static visualizations or like setting up an interactive tool that would allow them explorative?
Yeah, so it was mostly static visuals, not interactive, but they were writing code for them, yeah. I thought there was one more hand. Oh, yes?
Just a question where even though the control conditions, they did take more time, they're also writing code, so it will take more time. I don't know how much they spent like just observing their visualizations that they made. I don't know if you have those answers, yeah. But I'm curious about your, like, I guess, hypothesis on like why they were a lot higher, just taking into account maybe they spent the same time like looking at it versus all that extra 20 minutes was like writing this code. Was it something that they wrote out themselves that wasn't shown? Was there, like, what was going on there?
Yeah, so we weren't observing the participants, so I don't know what exactly was going on. But my hypothesis is that when they had to write the code to get to the visual, they paid more attention to the output than if the visual was already provided by an interpretability tool, whether that's interactive or static. That's just my hypothesis, though, yeah. Yeah?
So just a quick question on, you know, visualization literacy. Like, did you get any measure of, you know, I mean, it's counterintuitive that data scientists, visualization literacy, you know, like they'd be, you know, superb at interpreting visuals, but did you measure anything like that?
We had an exclusion criteria around machine learning experience and interpretability experience, where the question around interpretability experience was around visual explanations from interpretability tools. But we did not measure it beyond that, mostly because you know, there are some outputs from these, not particularly these tools, but in the control condition in particular, that are just static sort of number, not even visual outputs, right? So we weren't really trying to think too much about the visual component. It's just that was the nature of the state-of-the-art tool. So we felt that if anyone had used interpretability before, that was sort of, if they were in the state-of-the-art machine learning interpretability pipeline, they had used the visual ones, all of them. Yes.
I'm curious about the axis of like generalizability you want here. Like one axis is that this generalizes to other tools. That, you know, future tools, even if they gave perfect explanations, this would still happen, and you know, accuracy would be bad. The other axis of generalization is to people. Like okay, like the tools just are never going to get there, and you know, people are just going to be people. I'm just curious, like. Ultimately, is this a message of like optimism toward like, well, these tools can't do it, but maybe future ones could, or like even if given future interventions, this is still going to happen?
Yeah, so I think bounded rationality as a concept and as a theory that we know about cognition has existed for a long time, right? So that axis, I think, is somewhat covered already by this generalizable bounded rationality theory, right? Our goal was more to sort of make it more clear how that's affecting machine learning and interpretability pipelines for experts, right? So if any generalizability here that we cared about was in the tool design. Like, are these types of tools that are visual outputs of a certain kind, maybe made more interactive? What can we do on that axis of tool design of visualizations to account for the fact that things will always be boundedly rational? So we wanted to, the type of generalizability we were trying to tackle was on the tool axis that you mentioned, the first one, not the second one. Because no matter what specific tool you use, these are the three, maybe another couple more types of explanations that you get from all of them. They might be presented in slightly different ways, but the kind of heart of the information being presented is the same as these tools.
And someone could walk away from this study saying, okay, if we're going to be boundedly rational, given your results, we should just never use explainability techniques. Is that the right or the wrong conclusion from this?
I think it's somewhere in the middle where, at least in the paper about this, we talk about potential strategies, right? Because you're right that maybe the easiest solution is that we make people work hard for getting interpretable outputs. But you can also do that with these tools, right? It's just that the scale here was too easy with the visual explanations or too hard with the current interactive tools. So maybe the right answer is somewhere in the middle, right? Where we want there to be a level of difficulty, but we don't want it to be as cognitively burdensome as sort of how the interactive tools were. All right.
Let's let her continue.
Yeah, there's a little bit more here. All right, so the important question, right, that some of you also asked, what do we do about this? How do we enhance human-AI interaction going forward, knowing what we know about sort of the results that I've presented? So this is where we were looking for inspiration outside of technical fields entirely, right? We try to see what human factors might be relevant. How do we re-envision interpretability and explainability so that these human factors are a part of the conversation from the get-go? And the theory that we looked at was organizational theory. Now, you might ask, why organizations? What do organizations have to do with any of this, right? Organizations form when there's a need to collectively process information. At their heart, they're sort of systems of information exchange, where you work not only on your individual task, right, but you also work in teams. So you have to understand the tasks together as a team. There's a lot of shared meaning-making happening. And you work across the organization in different teams that all have the same goals. So if there's some way in which organizations have managed to handle the intricacies of human sense-making and cognition and still kind of be successful, there might be something there that we could learn from. And not just be successful, there's a subset of organizations that are all about safety. These organizations are called high reliability organizations, orgs like healthcare, air traffic control systems, naval aircraft carriers, nuclear power plants, where safety is critical, right? So they have metrics in place, measures in place, and practices in place that enhance the safety despite people being people and doing people things, right? So looking ahead, I wanted to take inspiration from these organizations. So this is sort of the set of projects that I'm working on right now, hopefully with students soon. I proposed this idea of inefficient AI for safe human-AI interaction. Now, let me start that off with an example, okay? So imagine a naval aircraft carrier. If you ever read a study on the flight deck on a naval aircraft carrier, if you were prioritizing efficiency, you would have maybe one person doing each job that's required on the flight deck of a naval aircraft carrier. But if you look at what actually happens on the flight deck, there's one person doing the task and two people just sort of watching them do the task for each task that needs to be done. There's a supervisor that looks over the entire deck, and then there's 2 to 3 people helping the supervisor. So there's a lot of redundancies and inefficiencies that these high reliability organizations add to their pipeline because to them, safety is critical. They can't afford to make a mistake. So sort of, going with that idea for human-AI interaction, here are some design ideas I have. So let's think about seamfulness. In HCI in particular, we talk a lot about seamlessness of integrating our product into people's everyday lives, right? And that's, in this setting for interpretability in particular, causing a sort of automated response where people quickly make decisions. So how do we introduce the right amount of complexity as we're introducing these tools into their pipeline? Similarly, can we induce skepticism in people? Can we make them question things instead of simply looking at information or simply parsing information? And can we help them engage in adversarial interactions? So the idea behind adversarial interactions comes from red teaming, right? So you sort of come together, put different people together on the same team with different expertise to attack the system to make sure that it's not going to fail. So how do we failure-proof these systems using these adversarial contestation sort of mechanisms? Some ways in which we're doing this for interpretability are, instead of seeing like a top-end important features visual, make it a conversation. And all of you are probably aware of large language models right now, which enable this sort of conversational format, right? But what's the right type of conversation? Is it a dialogue? Is it a question-asking setting, like the Socratic method, using that with AI and interpretability outputs, right? So testing out these different types of formats for conversation. And instead of, again, this is sort of making things more seamful, but you can also make people a little bit more skeptical by showing not just the top-end important features that the model did consider in making a prediction, but the bottom-end features that it did not consider important, right? And maybe you add random caution flags to the information that can be, again, randomly generated or system generated in the back end based on some anomaly detection or other analyses that are already being done by data scientists. So again, it's all about presenting the information, directing attention the right way, rather than completely changing what we think about interpretability from sort of scratch. You could also imagine enabling adversarial interactions by things like Slack, right? So you could put together people from different teams with different expertise, say before a model is deployed, a model engineer, a system designer, a front-end designer, a back-end designer, coming together to see these outputs about a system all together, right? So here's an example interaction that might happen. This is the same information as before. Someone's asking more about it, thinking more about it now that they're in a group setting, kind of going off of each other's ideas. The system seamlessly adds more information in the Slack interface, leading to maybe an information request from an individual on wanting to explore something a little bit more, allowing that also to happen. Here's a seamless example of allowing that to happen in sort of the conversation, recording context for other people in the conversation, coming back to the main setting and continuing sort of conversation with different people. So how do you put different people all together in the same setting to have a conversation about the failures of a model? Now, of course, inefficiency can be a potential solution here, but just making something inefficient is not always right? You can't just sort of make all interactions inefficient. When you're thinking about making something seamful, you also have to balance that with usability, like the interactive interpretability tools in our experimental condition were too cognitively burdensome to use, so they weren't a good solution. As you make people skeptical, they still have to trust the system, right? Because there needs to be some baseline trust. Otherwise, they just won't use it. And then, of course, you want to prioritize people thinking differently, but you also want them to have some shared cognition about the task, about the team, about the goals of the sort of project at large. So that's my very quick overview on how to use social theories to enhance human-AI interaction. Some of this work was stuff that I did at Michigan as a grad student, but I'm really excited to now continue doing it with undergrads and grad students at Minnesota, and sort of working with students who might be interested on similar topics. And I'm happy to take any other questions.
Okay, now you can go.
Sorry, this is pertaining to that particular CW study. Again, between the different groups, I was just curious if you had any gauge as to confidence in sort of subjective understanding of, or confidence in their own interpretations or in their responses.
That's a fantastic question. So we did measure confidence and other things like how much of a novice they were within the machine learning setting in general. And what's surprising is that people who were novices and had less confidence performed better overall than people who were experts and were more confident about their answers. So there's something to be said about this idea of inefficiencies, both at the people level and at the system level again. Yeah.
Thanks. And then sort of kind of a follow-up just in terms of the interactive condition. You mentioned sort of one of your hypotheses was that it was potentially too overwhelming. Were you able to gauge any sort of confidence dip too in relation to sort of these interactive systems? Or I'm just kind of reflecting and thinking when I use a really complicated or first encounter a complicated system, maybe within the time frame of a study, I might not feel really confident, but then over time, sort of learning and having time to sort of understand it, then potentially it could help improve my accuracy.
Yeah, that's another really good point. Unfortunately, for the purposes of the study, we weren't able to see longitudinal sort of interaction because it was a one-off sort of task. But that's something that I'm interested in more broadly is what kind of training do you provide people sort of from the get-go and as they sort of continue using these tools and how that might help mediate some of the effects that we see here. Yeah.
Thanks.
Yes.
For this study, I'm curious, whether there may have also been, people thinking what you might be testing. For example, if people think you're testing how good the system is, then they don't necessarily care as much about giving you the wrong answers. Whereas a control group that didn't have the system they were interacting with, it was almost like their reputation at stake. So they maybe actually tried harder to make sure they're giving the right answer instead of the other one.
Yeah, again, good point, and maybe it could be. I can't say for sure that it wasn't, but in terms of the instructions that we gave people to counter that a little bit, we told them that the task was just to the study was about performing an exploratory data science task with the help of existing tools. So they didn't think that we had developed these tools and we were asking for their opinion about our tools. Or, I mean, that's the only way we sort of even tried to mediate what you're talking about, yeah. Because I did not build any of these tools. I've used them and I've studied them and I've built on top of them, but the core tools were built by organizations. Okay, sorry.
So popular.
Please go ahead.
Based on your knowledge of just, I guess, other studies with these tools, I'm curious about the context and time people spend, with the cognitive load. So like I liked your visions of these things happening in Slack and maybe going across an asynchronous conversation. But then when I think about the individual spending 5 minutes, like I think it's your job. You better not be spending 5 minutes on it, unless maybe you're like an AI engineer. It's like 5 minutes before the meeting, and maybe prioritize that. But I'm just curious about your knowledge about that space. Like what does it actually look like?
Yeah, I think that's a really good question, and I'll tell you, part of the challenge in conducting research in this space is that data scientists work in organizations and their practices there might look very different from sort of what we study, right? We can try to create an environment that looks very close to how they're doing their daily work, but I mean, even recruiting participants for studies like these, right? If we're asking data scientists to spend their time doing this, we can't possibly pay them what they get paid in organizations where they do this as their job. So one way in which we incentivize people to treat this as an important task was to say, okay, we're not paying you for this, but we will donate a certain amount of money to a charity of your choice, right? Because when people think of doing sort of an altruistic, motivated task, they do it a little bit more seriously. But I don't know to what extent this would map to a person's day. When someone treats this as their daily job and sort of has their, whether or not they get fired, attached to the way they perform the task. So that's sort of going to be a control issue that's always going to be the case with research. Yeah.
Yeah, thanks for the answer. Yeah, just it's complex. All the motivations
yeah.
and bounded rationality aspects.
The nice thing is that bounded rationality has been studied in many, many settings. Maybe in this setting it hasn't been studied in a realistic organization, right? Because we're just starting out to do this. But in other settings, it has been studied in organizations. So I have some hope and confidence that it might still apply even in this setting. And we're just trying to answer the question of, well, how will it apply and what will help it, rather than seeing it again in a realistic setting like that.
Maybe one last question?
Yeah.
So this is also related a little bit to the motivation part, because I'm curious, because based on the setting, it seems like, okay, the human, whether it's an expert or not, a human could do something. The AI or the model, either XAI or the AI itself, it could do something. There's a huge issue of their incompatibility between the two of them. Right, and so I would like to ask if you can say a few words of saying that, okay, given I am a human worker, I'm working on something, what can I learn from the AI? For instance, I'm using this AI. It sounds like it's going to make me lazy, and my performance is going to go way low. Mm-hmm. So I don't want to use it, right? It's something similar to the scientist, right? Because if the scientist is going to be like, okay, given this AI, given this experimental AI, it's going to make me work faster, and it's going to make me some kind of performance boost. I'm going to get a huge pay salary, right? I'm curious to say, like, can you say a few words of like what kind of human workers gain from the system?
Mm-hmm. Yeah, I mean, again, a great question, and to some extent, we forget the time before this, right? So there was a long time in machine learning and AI when you couldn't see inside the black box at all. You couldn't get interpretable outputs at all, right? So our control condition tried to model that, but even that wasn't necessarily a purely control condition in that we still had helpful links for people to go get similar visuals, right? So sort of going back to when we had no help from explainable AI, it was a far more challenging task because there was just no information or very little information. So in some sense, there is a benefit, right, that explainable AI is providing, that we can at least now look inside the black box and understand what's going on. But to your point about us becoming lazy, having that's where I personally think this idea of introducing inefficiencies or inefficient interactions might be helpful, in that we don't need to change the information we now have, which is a good thing, but maybe we need to change how it's presented and how people have access to it and what kind of attention they're paying to it. I don't know if that answers your question, but it's just my thoughts on this. Yeah.
It's very hard to say, it's very hard to convince some kind of real user to say, okay, this system is really awesome, I'm going to use it.
Yeah. Maybe you don't pitch it as really awesome all the time. Yeah.
right, let's thank our speaker.
Thank you.